Right. Let's look at the question for the. It says let n be an element in the natural number set that does not have 0, and let k and x be integers. We define the congruence class k dash of integer k as the set which contains all integers that give x equal to k mod n. We now define a set which contains all these congruence modulos n. Part A says, for the operation that's been defined, show that this is a group, and also asks us if it is abelian. So like last time, fairly straightforward. Let's try to prove the 4 properties of a group. Let's start with closure. So let's assume 2 elements A and B. They are both elements in the set Zn. Let's use this notation. The question has provided us 2 notations that we can use. They're both equivalent. Let's use this. Then this, as it has been defined, is equal to this. What you must notice here is this was an element here, and so it was either 0 or something like n minus 1 dash or something in between. So was B. Their addition mod would also be an integer, because these are integers and the addition is closed under operation of the set integer, the operation of addition. So if you now mod n that value, whatever that is, it will remove a quotient of n, and so the remainder will always be something like 0, 1, so on and so forth until n minus 1. So we can be sure whatever this is actually an element of Zn. It's a fairly logical argument. And I think a logical argument here suffices. There's really not much more to be said, or something that can be said. I wish there were more algebraic, more simpler argument to follow, but there's a logical one. This is fairly trivial, but this has to be presented well. It has to be written well if it's being written as an answer. But here I just explained it. So that's that. So closure is proved. Let's go to associativity. Associativity. Again, I hope I'm spelling this correctly. I really need to look the spelling of associativity up. But anyways, in associativity, as I said last time, it's really just tedious. Don't really have to be clever for this, because you just need to set this up with the operation and prove that these two are equal. The left hand side and the right hand side come down to a statement that is equivalent. Again, this is by definition. Let's see. And this would be A plus B. And then this is A plus B plus C. Let me do this. We know that addition is associative in N, or you could say is a group. This is just a more formal way of saying this. I'm introducing this so that we all develop greater intuition about how to use formal mathematical language. And since we know this to be true, this is actually true, meaning this is associative as well. Let's now think about the neutral element. This is again fairly simple. You must find something here that returns A. In this case, that's obviously this. Why this? Because A plus 0 is A plus 0, this by definition. And this is just A, which is true. So that's a neutral element. And then the fourth one is proving an inverse. Now, as I said before, when we are trying to prove the inverse element, the last video talked about this, we are trying to get A plus some element so that it produces the neutral element again, which we determined was 0. Let's consider this as I dash. How can we prove that I dash always exists? Well, remember, A plus n minus A will always be A plus n minus A, this, which is going to be n congruence class, which is 0. Why? Because n congruence class is whatever gives n equal to 0 mod n by definition, and so this is just true. So I is equal to n minus A, where A is obviously an element from natural number set 0 and is less than the last element, which is n. So you have all four things proved: closure, associativity, neutral, and identity. Sorry, inverse. Actually, neutral itself is called identity. Yeah, there's that. And that proves that this is actually a group. So we have proved that this is actually a group. Let's now try to prove that this is also abelian. So for an abelian group, we have the last property, which is if this is commutative. We just need to prove that this is the same. So if you follow along, this becomes A plus B, this becomes B plus A. Clearly this is true, as addition is associative, and so the congruence class on top of it would also be the same, as this would come down to be x and x if x is equal to A plus B. That's a true statement. So we've completed part A. Let's now think about part B. We now define another operation where A cross B represents the usual multiplication in integer set. Let n equal to 5. Draw the times table of the elements. This. So this is the set which has all the equivalence classes for n5 excluding 0. Under this product, and show that this is closed and possesses a neutral element. Display also the inverse elements. Conclude that this is an abelian group. Alright, that's fairly straightforward. So let's take A here and let's take B here. Remember, this does not include 0, so it's 1, 3, 4. And these are all the elements: 1, 2, 3, 4. Let's now think about what is 1 times 1. So 1 is just 1 times 1. So that is 1. So this will be 1. And similarly, you can fill the other places. This will be 2. This will be 3. This will be 4. That will be 2. That will be 3. That will be 4. Let's think about this. This will be 4. Let's think of this. 3 times 2. 3x circled 2, this operation, whatever this is, will be 6. This equivalence class has to be reduced. So it's 6 mod 5. That is just 1. So that is 1 again. 3, 2 is 1 again. 4, 2, 8. 8 mod 5 is 3. So that's 3. 3 3s are 9 is 4. 4 3s are 12 is 2. 4 4s are 16 is 1. That's the entire times table. What we notice is for whatever option of A, B we take, the result is always within the set that was given to us, meaning it is indeed closed. Yeah, that should be sufficient. I'll close this here. Okay, so we have shown that it's closed, which I think was the first part here. The second part asks us to show that possesses a neutral element. There's no point in trying to go for a further proof. Let's just look at each element. If we take A and an element E, it gives A again. In this case, that is clearly 1. As when you take any value of A and the next element is 1, it returns the same value. So 1 is 1, 2 is 2, 3 is 3, 4 is 4. So clearly it's 1. That is E is 1. Yep. So we've just proved that there is also neutral element. Let's now look at an inverse. So does an inverse always exist? Well, again, we can just go back to this. There's no real need to do any of the hard work again. No need to actually prove it. We can just look at this again. So an inverse will exist. Let's look at these values. You must multiply. So the definition of an inverse, just for the sake of original mention this here, is that you must be able to find an I such that this gives 1. Alright. So for each A that is 1, 2, 3, 4, there should be an element here that gives 1. 1 times 1 is giving 1. 2 times 3 is giving 1. 3 times 2 is giving 1. And 4 times 4 is giving 1. So we have an element that gives 1 for each of these 4. It happens to be different for all of them, as you can see. But we do have such an element I. Yep, so there is also an inverse element that exists. The last thing we can prove here is that to show that this is a group. So you have proved closure, you have proved identity inverse. This is clearly associative as well. So let's prove that here. As this is the same as E times B, which is the same as this, which is the same as this. So clearly associative. So this is actually a group. No, sorry, this is actually the argument for commutativity. Commutative. And it is also associative. As you have this equal to this. So if you change the order of operations, you get something like this would be this is again clearly true, and so you can argue that this is also associative because when I tried to associate them in different orders, the result was actually at the end of the day the same. So you can say with complete confidence that Z5 is an abelian group as it satisfies all 5 criteria. Righto. In part C, we have been asked to prove this is not a group. Is not a group. How can you prove that? Well, basically you need to find a contradiction to one of those 4 key properties. So that would be associativity, the fact that it's closed, inverse element, and identity element. So maybe we can find proof that this is not actually closed. So let's think of 4, which is clearly an element of Z8, this, and 2, which is also an element of Z8, excluding 0. Remember, Z8 is the set 0, 1, 2, 3, 4, 5, 6, 7, where these are the congruence classes. And remember, if we go 4 times 2, that gives you 8 mod 8. So that is just 0 bar. But 0 is actually not included, as this has been removed in the definition. And so you have 2 elements that are part of the domain, and yet when the operation is done on them, they give a response that is not part of the set, and so this is not closed. The fact it's not closed means it's not a group. Simple. Yep, that's simple. Let's think about part D. Yes, let's think about part D. Part D is interesting and should be fairly obvious if you understood part C. Part D says, recall the Bezout theorem states that 2 integers a and b are relatively prime if and only if there exist 2 integers uv such that they can be written in such a linear combination. Show that Zn is a group if and only if is prime. So if you remember the last example, what happened was we found 2 elements in here which multiplied to give n, and therefore their modulo gave 0, which was reduced and removed. So the thing is, if n is prime, no elements of Zn can be multiplied to give n. Therefore, the product will always be closed. We already know that it is always associative, commutative, neutral, inverse from previous part. Therefore, Zn is a group. Yeah, that's sufficient. Yep, that's all. That's all for today. Thanks.